In this lecture, we're going to look at two different things. One is multi-class classification. We've been so far looking at classifiers applied only to problems where we have two different classes. Now we're going to see how to extend that to an arbitrary number of classes. But the most part of this lecture will focus on the decomposition of the error into bias and variance. This is something that is not particularly useful in general for practical applications, but is important for understanding the sources of the errors we have when we compare our predictions with the data, and also to understand what I will be talking about in the next lecture, which is using ensemble models. So we're going to see how to, what are these concepts of bias and variance, how we can try to compute them or estimate them and decompose the error into these two terms and see how they relate to the problem of underfitting and overfitting. But first we'll start with multi-class classification. So for some classifiers, it is trivial to handle multiple classes. For example, we saw k-nearest neighbors, which is a classifier that stores the training data and then outputs the majority class from the k-nearest neighbors. So independently of how many classes you have, as long as the classes are labeled in this training set, you can use this classifier for any number of classes. You also implemented the naive-based classifier, and as you can see, we classify each example into the class that maximizes these probabilities. So the prior probability of belonging to the class, and then the sum of the logarithms of all the conditional probabilities of having those values in each feature if it belongs to the class. This is trivial to extend to any number of classes because we just compute this for every class and simply pick the one with the largest value. So it doesn't matter if there are two classes or three and so on. But let's see how we can adapt other classifiers to this situation where we have more than two classes. And to do that, we'll use this example. This is a classical example in machine learning, the iris dataset, which is a dataset with 4 attributes that describe these flowers. So we have the sepals and the petals, and we can measure the length and the width of each. These are the 4 attributes. And there are 3 classes because we have 3 species of this kind of flower. So Setosa, versicolor, and virginica. And we can we can try to predict from the sepal and the petal dimensions which class each flower belongs to, because the flowers are slightly different and they have different proportions of dimensions in sepals and petals. So this is the data set projected into 2 dimensions. So I'm only using the sepal width and length in this case. The actual data set has 4 dimensions, which makes it hard to plot and to illustrate anything. So I just threw away 2 of the features and I kept these 2 just for illustration. So we have the 3 different classes here represented with 3 different colors, and as you can see, they are distributed in fairly different ways along these features. So if we train a k-nearest neighbors, for example, with a neighborhood of 15, this is what we get. This is simply at each point we are classifying into the class that has the majority of examples within the 15 nearest examples to any point. So if we have a point here, we take the 15 nearest examples and we classify it in the majority class. That's why this is red. Here we have green because there are some green examples there, and probably also it catches some green ones over here. Here they are mostly green, blue, and so forth. So for k-nearest neighbors, it's not a problem to extend the same idea of classification with 2 classes and extend it to 3 classes. We just take the majority vote and it works all the same. With linear discriminant classifiers, this is a bit more complex, because if we take, for example, a support vector machine or a neural network or logistic regression in the way that we trained it, if we are trying to determine where to place a hyperplane that separates 2 parts of our space of features, we cannot do that for an arbitrary number of classes. So if we draw a single line here to separate 2 parts of this plane, We cannot do three ways classification with that. So let's think about different ways of approaching this problem. One possibility would be to train classifiers to distinguish one class from the rest, everything else. Another one would be, so this would be the one versus the rest possibility. Another possibility would be to consider all pairs of classes and train classifiers to distinguish between each one in that pair. So we'd have a number of classifiers equal to the number of classes multiplied by the number of classes minus 1 divided by 2, because this is the number of different pairs that we can form with k classes. Or we can just train a number of k classifiers, each one trained to distinguish one class versus the rest, and then use the maximum of the value of the decision function of the classifier. So let's look at the pros and cons of the different approaches. I'm going to detail them a bit more so to illustrate better this problem. But the main problem here is to try to extend classification with a linear discriminant classifier, so one that splits the space of features into two parts, and use that to classify more than two classes. So let's see this possibility. We can create k minus 1 classifiers. So let's suppose k is 3 because we have 3 classes. So we create 2 classifiers, and each one is trained to distinguish between one of the classes and everything else. So let's say for all classes from 1 to k minus 1, so classes 1 and 2, for example, we can set this class k as the label 1, and everything else as the label 0. So the classifier can distinguish if it's of the class that belongs to that classifier, or if it's not, if it's one of the other classifiers. And then we can assign the class according to each classifier considers an example to belong to that particular class. If none of the classifiers, if none of these k minus 1 classifiers thinks that the example belongs to its class, then we attribute the class that is left out, class k, the last one. So this would be the idea. We can create one classifier to distinguish between setosa and everything else. So if it's on this side of the line, this one says it's setosa. Then we can create a classifier to distinguish between versicolor and everything else. And now we could think of classifying any example in this way. If this classifier says it's setosa, then it's setosa. If not, then if this classifier says it's versicolor, it's versicolor. If neither of them claims the example, then it's virginica because it's the one that is left out. So this would be one way where we could extend binary classification into n classes. The problem here is that we have ambiguous areas. For example, any point that falls here will be classified by the setosa classifier as setosa and by the virginica classifier as virginica. So we would not know which one we should assign an example here to. There is a problem if we have this approach. One advantage would be that we need fewer classifiers than classes. So for 2 classes we only need 1 classifier, for 3 classes we need 2, and so forth. But with more than 2 classes we have these ambiguous areas where more than 1 classifier is claiming the class of that point. So let's see if we can solve this by using classifiers for all pairs. So basically, in this case, we need 3 classifiers, one between setosa and versicolor, one between setosa and virginica, and one between virginica and versicolor. So basically, we have 3 classifiers to distinguish between red and green, red and blue, and blue and green, red and blue, and red and green. This way we can tell if where a point belongs to by classifying it with all the classifiers and seeing what they conclude. The problem is that there are regions where the classifiers disagree, so they give us different classifications, and again we have these ambiguous areas where we don't know how to solve this problem. So this is why usually the extension of binary classifiers to n classes, or k classes in this case, is done with this one versus rest classifier, or one versus all. This is the general approach where we create one classifier for each class, and instead of simply looking at the classification, we need the classifier to give us some value for the decision function. For example, the distance to the discriminant plane, or a measure of probability, or something like that, a continuous measure that we can use to assign how strongly or to estimate how strongly the classifier is assigning a point to that class. So, for example, in this case, we could train a classifier to distinguish between setosa and everything else, versicolor and everything else, virginic and everything else. But then, instead of just looking at the classification, we would take the maximum of the decision function, and that will avoid those problems of ambiguities, and what we get is this result. So this is where the classifier for versicolor has a higher maximum than the other two. This is where the classifier for virginica has a higher maximum, and the same for setosa. So this is the most used approach when adapting binary classifiers, ones that have this, for example, that separate the space of features in just two parts, and adapting them to multiple classes. So the advantages of this is that since we are classifying using the maximum of the decision function, we don't have those ambiguous regions because we have this continuous value here. Of course, we need classifiers that give us this value, this continuous value for the decision function. There are some disadvantages of this type of classification because it's based on training classifiers to distinguish one class from everything else. So all these classifiers are working with data that is very unbalanced. So if you have, for example, 10 classes, on average, each class will only have 10% of the data. So when you train a classifier to distinguish that class from everything else, you are dealing with very unbiased data. And then there is the problem that we are comparing the decision functions, for example, the distance to the hyperplane or the estimated probability or something like this. We are comparing the decision function of different classifiers, but it's not necessarily the case that it's always in the same scale, or it can be really compared. So it's a bit questionable why the line is exactly there, just because one has a higher value than the other on the decision function, if those values may not be exactly on the same scale. So this is not a perfect solution, but it's a very convenient one, and it's a very simple way of using any classifier that works for two classes, and we can use it for any number of classes. There are some special cases, for example, logistic regression. You can do this with logistic regression because logistic regression gives you the probability of belonging to a class. So we can use that probability to get the maximum for each point, and use several logistic regression classifiers in combination to classify for an arbitrary number of classes. But the cross-entropy error function that we are minimizing in logistic regression can be extended for an arbitrary number of classes. So actually the logistic regression can have this multinomial option where the function that is being optimized takes into account all the classes, and the classification also takes into account all the classes. So in scikit-learn you have these two options. You can use logistic regression for more than two classes, specifying that you want one versus the rest. So in this case you are training as many logistic regression classifiers as the number of classes that you have, and then it will classify automatically according to the maximum of the decision function, or the probability. Alternatively, you can train logistic regression classifier but with this multinomial extension to an arbitrary number of classes. So in this case it will only use one multinomial logistic regression. The training is a bit more computationally demanding, but then you have the logistic regression trained for all these classes. So there are different classifiers that can adapt more or less easily to more than 2 classes, but you always have this possibility of using the one versus the rest for classification. And scikit-learn offers this possibility. It has implemented the one versus the rest classification. For neural networks, you can also adapt the neural network, for example, multi-layer perceptron, in order to do to classify more than 2 classes. So if you have 2 classes, you only need 1 neuron in the output, and you use the sigmoid activation function that basically can be interpreted as the probability of belonging to one class. So if it's over 0.5, it belongs to that class. If it's below that, it belongs to the other class. If you have k classes, you can use k output neurons, so 1 for each class, and then the output of the network can be computed using this softmax function. So basically, you take the sum of all the activations, all the sigmoid activations, and you normalize it. And the advantage of this is that you will get a vector at the end which has these properties. So each value in that vector has a number between 0 and 1, and the sum of the values in the vector is 1. So we can interpret this vector as giving us all the probabilities of belonging to the first class, the second one, the third, and so on. And then we can classify as according to the class that has the higher probability there. So this is an adaptation that you can implement in the actual network. Instead of having only one output neuron, you have as many as the class is necessary. And using this softmax function, we can interpret the output as the probabilities of belonging to each class. This general solution of one versus rest is implemented in scikit-learn. You have this class, one versus rest classifier, that you can use to encapsulate the one versus rest approach. So you give the object that serves as template for all the classifiers that's going to be used. For example, in this case, it's a support vector classifier, the one that we saw last week. And we can specify the kernel, the parameters for the kernel, the regularization, and so on. So clones of this classifier will be used to train for each class, and then the classification will be done according to the maximum of the decision function on this classifier. So you'll use this one versus rest classifier as if it was just a simple classifier like all the others. You can use fit, predict, score, and everything else. So this one versus rest approach is very easy to use in scikit-learn because it's implemented there, encapsulating a number of classifiers, the number necessary to classify all the classes. So this is an example of classifying this iris dataset using the one versus rest classifier with this support vector machine, this support vector classifier with these hyperparameters. So this is the result that we get in the end. Okay, so this is for multi-class classification. The general message is some classifiers are very easy to adapt to more than 2 classes. In other cases, you can use this one versus rest approach, and it's very simple to use in scikit-learn because it's encapsulated there in the one versus rest classifier. So now let's look at some aspects of the errors in classification, and we're going to do this decomposition into bias and variance. So first, bias, what this means. So we saw so far this notion of having unbiased estimators, and statistically bias is an average difference between the estimate and the value we're trying to estimate. So adapting that concept in this case, let's suppose that we have data that has these points. So let's look at this point here, and we fit a model that cannot quite accompany the distribution of the points. So our model is underfitting because it cannot adjust very well to the data, for example. And so we are predicting for this value here, if the input is 4, the feature is 4, then we are predicting a value that is higher than what it should be. This should be the real value we are predicting over there. If we train our model over different samples of this kind of data, so let's suppose that each time we sample from the universe of data points, we get something like this, and we have here in different colors different samples, different data sets, then our model will try to fit this data but never quite manage it, and we can see that we have an average of our predictions that is overestimating the actual value that it should have here. So this is the bias. It's the average difference, or the difference between the average of our predictions and what the value should be. So this would be the bias for this particular point, the average of our predictions, and then subtract the actual point. But we can extend this also to compute the average bias over all examples for the model that we have. So basically, we can consider that the bias at point n is the difference. In this case, it's the square of the difference between the prediction for that point and what the target value would be. So remember that sometimes the bias is represented as bias squared, but this is not because we are squaring it, it's just because it's the square of that difference. And we can compute the bias for the model by averaging for all examples. So in this case it's not quite the bias for the model, but the bias for one of these hypotheses. For example, we could average over all the points, or we could consider at this point the bias of the model by looking at the different hypotheses we are obtaining when we consider different samples. So basically what we're doing is we are measuring the bias from the point and averaging over all the points, and then averaging over all the hypotheses that we have. Variance is a different concept, but it's similar to the notion of bias. Let's suppose that the model is overfitting and it adjusts too much to the training data, and when we train the same model over different samples, over different data sets, we obtain a large variation in the predictions. So here we can see that for this value of 4 in the features, we have many different predictions here going around wildly around this region. So we can measure the variance or the dispersion of these predictions. So basically we take the average point of all the predictions and we measure the square of the difference between each prediction and the average. So this is the average prediction over a large number of hypotheses obtained from the same model, but using different samples from the universe of points. And this is each prediction from each of the hypotheses. And this gives us the idea of the variance, which is a measure of how wildly are the hypotheses changing in this point as we retrain our model with different data samples. So if you want to do this for the model, we just average this over all the points. So we take for the model a large number of hypotheses, we measure the variance for each point, and then we average that over all the points, and this gives us the variance for the model. So we now have these two measures. Basically, bias, we are measuring the distance between the actual value and the average of the predictions that our model makes when we train it with different data sets. So considering different hypotheses, we average them and we measure the square of the difference between that and the true value of some point, and then we average that over all the points. The variance is similar, but instead of measuring the average distance to the true value, it measures the dispersion of our predictions. So we are measuring the distance between each prediction and the average of all the predictions. So now we have these two measures that tell us, on one hand, how our model tends to move away from the correct prediction. This is for bias, and for variance, it measures how wildly our model is dispersing the predictions. Okay, so now we can use these two measures to understand what the model is doing on average. Note that these are not measures for any single hypothesis, because when you are measuring bias, you are considering the average prediction over a large set of hypotheses trained from the same model. And when you are considering variance, you're also considering the dispersion of the predictions relative to that average. So bias and variance are measures of the model and what the model generally does when we train with this kind of data, and not measures of any single hypothesis, because we need to average this over a large number of hypotheses. But with these two measures, we can now understand what is happening when we have things like underfitting, overfitting, and what are the sources of error. And this is the idea behind Bias-Variance decomposition. Let's suppose that we have a squared loss function. So our error function is the square of the distance between predictions and the target value. So we can decompose this into these two terms. The expected value of our predictions minus the expected value of the data that the values that we have in the data. So these E here are averages, are expected values, and then we can consider add to this the average of the square of the difference between each prediction and the average of the predictions, and then this additional term which is the expected or the average squared difference between each of the values we have in our data and the average of the values. So basically this is bias, because this is how on average our prediction is distancing itself from the actual values. This is variance because it measures the distance, the average distance between each prediction and the average of all the predictions. And this is basically noise, because this is just about the data itself. This is about the true values in the data that can fluctuate, and we can consider that to be noise that is outside the control of our models. So we can think that error will be if we disregard the noise in the actual data, because that is not relevant for adjusting the model or choosing models or understanding what the models are doing, we can consider that the error will be the sum of this bias and variance. Now, the problem in practice is to try to compute this bias and variance, or to estimate bias and variance. We need several training sets, because we cannot do this kind of computation with only a single set of data points, because then we cannot compute the average of the predictions of the hypothesis the model produces over that kind of data, or compute this dispersion of those predictions if we can only get one hypothesis and one prediction for each point. So for bias-variance decomposition, we need to obtain a large number of data sets in order to be able to compute these values. Since we only have one training set and we cannot reasonably expect to obtain data at will, we need to use a resampling method. So this is where bootstrapping comes into play. We're going to also use bootstrapping for other things. We'll see in the next lecture. But the idea here is that we have one training set, one set of n examples, n points, and we're going to generate replicas of those points, of that set, by choosing points at random. And the reasoning behind this is that the data set that we have, the training set that we have, was chosen at random from a universe of possible examples. If we now pick at random from the training set, we should get the same distribution of values as we get when we sample from that universe of possible points. So sampling from our training set would be a good replacement for what would be ideal, but we cannot do, which is to sample again from the universe where the data was supplied. So this is what we're going to do. We're going to sample at random with replacement. What this does is, since we are choosing points at random, sometimes we pick the same point again. And so, since we are creating replicas with the same number of points, if we pick the same point twice, there is one other point that will be left out of the set. So each replica will have a different combination of points and will result in a different hypothesis when we train our model. To estimate these errors, we're going to do everything, so all these estimates outside the training set. So we can use, for example, a test set or a validation set, and we create the replicas and we measure the bias and variance outside those replicas. So this is just an example of how we can create the replicas for bootstrapping. We have our the data that we have here, and we can create a matrix with this number of rows for all the samples that we want. And then, this actually, it's a three-dimensional matrix if our data is bidimensional. So this would be layers. You can imagine this as a stack of matrices. This could be, for example, 500, a stack of 500 layers. Each layer has the same shape as our data. And now, for each of these layers, we're going to fill it with a random sample of our points. So our points are in the rows of our data. We create an array of integers with the same size as the number of rows in our data, and also ranging from 0 to the number of rows in our data. So basically what this is it's an array of integers that gives us at random what is the row corresponding to each of these points. So we're going to take the example in row 10, then the example in row 5, then the example in row 52, and things like that. So this is all at random, and we're going to put that in this sample. So we are iterating through all the different samples, the different replicas in our bootstrap set of data sets, and we are copying the data into that particular sample. So now we have a large set of training sets, all generated from the original one, but containing random samples of points, some of them missing some points, others missing other points. So they're all different combinations of points, but they all have the same distribution approximately because they are all obtained from our training set. Okay, so now we can do, for example, a polynomial regression and try to decompose the error into bias and variance in this case. So we have our training sets, which we obtained by replicating the original set using bootstrapping. We have a test set. This is a different set of points where we are going to measure all these errors. And what we're going to do is, for each replica, we're going to fit a polynomial of some degree. So we have the degree specified here. And now we're going to predict the values for the test set using that polynomial. So what we're doing here, suppose that we have 500 replicas, then we will have, for all the points in the test set, or for each point in the test set, we have 500 predictions obtained by training the same model, because it's the polynomial with the same degree, but each time training it on a different replica of the training set. So what we're doing is we are obtaining different curves because the training set, these replicas are slightly different, and for the different curves we obtain the prediction for the test set. Okay, so now we can compute the mean of all the predictions for each point. So if we take the mean of the predictions in the direction of the rows, we have the average prediction for the first point in the test set, then the average prediction for the second one, and so forth. So the bias we can compute for each point as being the average prediction minus the actual value of that point and then squared. This would be the bias for each point. It's a vector with the difference between the average of the predictions and the actual value of the point. And now we can compute the bias for the model as just the average of the bias for all the points. For the variance, we can use this formula. We can take the predictions minus the average of the predictions. So this will compute all these differences between each prediction and the average. We square that, and then we take the mean to obtain the variance for each point. And again, we average that to obtain the variance for the model. So these are just writing in Python the two expressions that we saw earlier. The important trick here is that in order to be able to obtain these statistics, the different predictions and the averages and so forth, we need to use a large number of replicas of our training set in order to train the same model with different sets of points and see how the curves will change, how the hypotheses differ between those sets. Okay, so doing this, we get the bias and the variance, and now we can compare what happens when we change the degree of the polynomial. So this is the degree of the polynomial for this data set. This in green is the bias. As you can see, the bias is large when we have underfitting. So on average, it is making a prediction that is falling away at a certain distance of the actual value, but when we increase the size of the polynomial, this tends to go down. The variance, which is the dispersion of the predictions, tends to be low when we are underfitting, but then it starts to shoot up when we overfit. And if we add the two to give us the total error aside from any noise in the actual data, so this is just the contribution for our model, we can see this typical valley-shaped curve that tells us that we are underfitting here, overfitting here, and here it should be the best values for the degree of the polynomial. So note that what we did previously was to consider that underfitting in this side because the model could not fit the data, could not adjust to the data well, overfitting because it was adjusting too well to the training data, but we really had no obvious reason in the plot to distinguish between underfitting and overfitting, because that was just having a high error or high error here, unless we looked, for example, at a training error. But now we can understand this in the different way because we are decomposing the error in these two contributions. So basically, when we are underfitting, the problem is that on average, our model is producing hypotheses that fall away from the value of the point. And when we are overfitting, the problem is that our model is having a very large dispersion in the predictions. So the predictions vary a lot from hypothesis to hypothesis if we train with different data training sets. Okay, so this would be the one with the lowest total error, which basically is what we can also do with cross-validation and things like that. So bias and variance decomposition is not a practical way of selecting the best model, but it's more a theoretical approach to understand these different contributions to the error. Okay, with the classifiers, this is a bit different because we've been looking at regression with a quadratic error function. With classifiers, we can consider, for example, to have a 0-1 loss function, which is that if we are making a mistake, then we penalize. If we don't make a mistake, we don't have a penalty there. So assuming there is no noise, the bias for the point will be this loss function, which tells us 1 if it's making a mistake, 0 if it's hitting it right, and this would be the mode of the predictions. So the mode is the majority vote. So suppose we trained the classifier 50 times with 50 replicas, and now for each point we can see the majority vote of all those different hypotheses that we got. So this would be the mode for the classification and the true value, the true class of the point. So basically, bias is 1 if the majority vote is wrong. So if the majority vote is different from the actual class, this loss function tells us returns a 1. The unbiased is 0 if the majority vote is correct. So if the most of the hypotheses are voting for the correct class, then bias is 0. The variance will be the expected value, or the average, of the loss that we have for individual predictions. So this would be the prediction for point I of one of the classifiers and the actual value for that classifier. So when we do this for all the classifiers and see if each one of them is predicting the mode of the predictions of all the classifiers and the prediction of each classifier. So what we're measuring here is the expected difference between the majority vote and the vote of each classifier. So suppose that all classifiers are voting for class 1. In that case, the majority vote is class 1. All the classifiers vote on class 1, and so the loss is always 0. They're always voting along with the majority. And so the expected value here would be 0. So if all classifiers are voting for the same thing, then the variance is 0. But if say, just a little more than half of the classifiers are voting for one class, and the others are voting for another, we will get a variance of 0.5, because on average about half of them would disagree with the majority. So this is what the variance the range that the variance can take. If all of them vote for the same class, we can have a variance of 0. If we have two classes and nearly half of them vote against the majority, then we approach 0.5 on the variance. Now, one complication here is that if bias is 0, that is, if the majority vote is correct, then variance is increasing the error, because the more classifiers disagree with the majority, the more the expected error will be. However, if the bias is 1, that is, if the majority vote is incorrect, then the variance decreases the error, because if the majority is wrong, then the larger that minority that is disagreeing, the lower the error will have on average. So for classifiers, this gets a bit more complicated in that to estimate the error here and decomposing it into bias and variance, we need to consider the error contributed by the bias, add the error contributed by the variance for those points that have no bias, that is, for those points where the majority vote is correct, and then subtract the expected the variance for those points that are biased, because those points for which the majority is wrong, it's good to have a disagreeing opinion in those cases to reduce the error. Okay, so let's see quickly this example. We use k nearest neighbors, for example, and optimize the number of neurons of neighbors decomposing into bias and variance. So again, we obtain these samples by bootstrap. We have the training sets here. We're obtaining them by bootstrapping. We are looping through all the samples. We are training the k nearest neighbors classifier for each of the samples, the training set, and we are computing the predictions on the test set. So when we finish this, we have for each point as many predictions of the class as we have replicas created from our training set. So now we can compute the statistics here. We're going to get the majority vote, so the main predictions, by using the average of the predictions. So let's assume these classes are 0 and 1. We take the average, we round that, and if the majority vote for each one point is 1, we get we round up to 1. If it's if the majority if the majority vote is 1, then this will give us a value that is higher then 0.5, and so it rounds up to 1. If most of them give the class 0, then when we average, we'll have something that is below 0.5, and this will round to 0. So here we compute for each point what is the majority vote over all the classifiers we obtained by training over all these replicas. Now we can compute the bias by comparing the majority vote, the prediction, with the actual class. So we can take the absolute value of this difference. If it's the same, the difference is 0, so there is no bias. If the majority vote corresponds to the actual class in the test set, the bias is 0 for that point. Otherwise, the bias will be 1 because there will be a difference of 1 between the two. Okay, so we have the main prediction, the bias per point. Now we can compute the variance for each point. And the idea here is that we're going to look at the differences between each prediction and the majority vote. So the variance is measuring the disagreement relative to the majority on average. And now we take the two contributions of the variance. So in those cases where the bias is 0, we have the unbiased variance, and we add up the unbiased variance, and we divide by the total number of points. And then for the biased variance, we do the same, but we use the variance for those cases where the bias is 1. So these are the two different contributions of the variance, because we need to separate the case where the majority is wrong. So if the majority is wrong, having a variance there is good because it reduces the error on average. But if the majority is right, then variance is bad because it's increasing the error. So this is what we do here. We return the bias and the two contributions of the variance, one in positive and one negative, depending on whether there is bias or not. So this would be the example for k-nearest neighbors for the first 15 values here. You can see that we have a high variance here at the beginning when we use a small number of neighbors. Then it starts reducing. Eventually we can have different effects because of sampling and of much variation in the different hypotheses, but we can see that the bias is increasing. So as we increase the neighborhood, we keep increasing the bias, and this basically ends up with the total contribution for the error, which means that we have the ideal point around here at 5 neighbors. More neighbors, we are underfitting. We have bias keeps increasing, and fewer neighbors, we start overfitting because then the variance is contributing more to the error. So this is basically how we can decompose bias and variance and look at what's happening to the error. So this would be for the best number of neighbors there, estimated by the bias and variance decomposition. So in general, one important thing to look at here is that we can reduce bias by increasing the power of the classifier to adjust to the data, and so it will tend to be less stiff, for example, and less bias in the predictions. The average will start to move more closer to the actual point. However, when we do that, we tend to increase variance, because as we increase the power of our model to adjust to the data, we start increasing the dispersion of the predictions when we train it with different data sets. So this is the bias variance trade-off, and in general, you need to find the best trade-off between the two to select the best model. Note that bias and variance decomposition, I only talked about it now because this is important for understanding what is happening to the model itself, and it will be helpful to understand some things we're going to see next. But this is not something that you're going to use in practice, because in practice what we need to know is how the error is changing over the change in model or some meta parameter, and this is much easier to compute using cross-validation, for example, than trying to do bias and variance decomposition, because you need a large number of samples, you need to use bootstrapping and so on. So this is not something that we're going to do in practice when solving actual problems. But this bias variance trade-off, it's important to understand because it's a strong limitation on what we can do with the classifiers. If we make them, or with the models in general, if we make them too stiff, we increase bias even though we decrease variance, and if we make them too powerful, we increase variance while decreasing bias. So we need to find the optimal combination of the two, but we cannot go too far to one side of the other. So to sum up this part, we saw multi-class classification. This was the easy part, just the extension of classifiers to more than two classes. And we saw these two concepts that are important, bias and variance. So bias is the average deviation from the true value. If you train your model with different samples from the universe of possible data, and then you measure the average deviation from some point, you are measuring the bias. This is especially important when the model is underfitting, because then it cannot fit the data adequately and will tend to give us on average a large error there. Variance is the dispersion around the average prediction. So the more powerful the model is, the more it tends to jump around in different hypotheses when we train with different training sets. Note that in classification, variance may increase or decrease the error depending on the bias on that point. So if the point is being misclassified by the majority of the hypothesis, then a larger variance is better than a lower variance, because it means there is a larger minority that is classifying it correctly. On the other hand, if the majority is classifying the point correctly, then having a larger majority a larger minority classifying it wrong will increase the average error. And bias and variance are related to underfitting and overfitting, because in underfitting bias tends to dominate, in overfitting variance tends to dominate. So these are some sections of the books that you can read for a bit more on this, and optionally you can read this paper which explains the bias and variance decomposition for classification and so on, and it's the paper in which I based myself to give you this example of bias and variance decomposition in classification. Okay, so let's take a short break, and at 5 o'clock I'll continue with the second lecture.